Okay, so let's now move on to the third problem, which is also my favorite problem on this whole paper. So when you first look at it, you are asked to basically find the number of subsets such that the sum is a multiple of p. So this kind of gives a combinatorial idea while also having a flavor of number theory inside. But in fact, if you're actually aware of complex combinatorics, this problem is actually very manageable and surprisingly easy for our problem 3. So my approach here will to be basically just compute a fine expression for a pk where k is a positive integer. And actually, as we vary across the multiples of p, we'll be able to find a suitable multiple of p for a fixed k such that the whole expression is a multiple of p too. So let us firstly find the expression for APK, I guess. Firstly, consider this polynomial. Let's call it fx. And the polynomial is 1 plus x times 1 plus x squared until 1 plus x to the power of pk. And suppose that when we expand this out, we'll get this following expression. Sorry, a1x, a2x squared, etc., etc. So basically, APK is equals to the sum of the coefficients wait, sorry, it shouldn't be ij, it should be ip. So basically, APK is the sum of the coefficients of x whose powers are a multiple of p. And this makes sense because when you look at a polynomial again, you can kind of think of x as the numbers from 1 to pk, where the numbers are the powers of x. And then you think of 1 as not including that number in the set to begin with when you create a subset. So when you combine, when you take the product of two x's with different powers, you're basically taking the sum of the powers, right? Which is equivalent to taking the sum of the numbers in the subset. So we have basically reduced the problem to this. Now I'll be using complex combinatorics to actually find a way to evaluate the summation of AIP. Okay, so before we start, we need to define the complex number. So we'll let the complex number be the number sigma, and it will be equals to e to the power of I 2 pi divided by p, where p is the prime. So this is like a magical expression which you should perhaps memorize or take note of in the future. So my claim will be 1 over p times the summation of f sigma to the power of j, where j varies from 1 until p is equals to the summation of summation of the coefficients of x's whose power is a multiple of p. So I'll prove why this is true. The proof goes as follows. we basically note that the left-hand side is basically equivalent to this, which is 1 plus A1 sigma j plus A2 sigma 2j, etc., etc. And now instead of summing it based on the sigma value, we try to sum it based on the coefficient itself. So it will become 1 over p times the summation of ai. Wait, sorry, we cannot forget to include the p, but the 1 term, sorry. So it'll be 1 plus 1 over p summation of ai times sigma sigma to the power of I plus sigma to the power of 2i until sigma to the value of pi. And from I, and so you have to split this into two cases. So if p does not divide I, we can evaluate the sum of the sigmas, which will just give us ai sigma I until sigma p I will be equals to ai times sigma p plus 1 I minus sigma I divided by sigma I minus 1. And we should take note that sigma p is basically e to the power of I 2 pi divided by p times p, which is equals to 1. So this will evaluate to ai sigma I minus sigma I divided by sigma I minus 1, which would be equal to 0. This is for I not divisible by p. However, if p divides I, it's a completely different story, since we'll have sum ai sigma I pi, and since sigma p is equals to 1, this just gives us p ai. So we'll have that 1 over p sum p j equals 1 f sigma j will be equals to 1 plus 1 over p sum pai for I which divides p, which is just equals to 1 plus sum p divides ai, which is basically equals to sigma sum to z plus AIP. Because we're taking into account I equals to 0 here. Wait, so I guess it shouldn't be z plus, it should be non-negative integers. Sorry. And f sigma to the power of j. What I want to do is to actually evaluate what f sigma to the power of j is. So f sigma to the power of j is basically just equals to 1 plus sigma to the power of j times 1 plus sigma to the power of 2j all the way multiplied until 1 plus sigma to the power of pkj. So how would you evaluate this? Okay, so we have to actually split this into two cases. When j is equals to p and when j is not equals to p. Let's consider when j is not equals to p first. So j not equals to p. Case 1. So if j is not equals to p, notice that sigma j is equals to e to the power of I 2 pi j over p. And so basically like all of these terms are being shifted by a factor of 2 pi j over p. And this will cycle every p times. So we'll go through all the p roots of unity and then cycle through it k times in total. So this will evaluate to 1 plus sigma 1 plus sigma squared until 1 plus sigma to the power of p to the power of k. And you may be wondering, how do I evaluate this term here? Well, it should remind you of the formula for, the roots to the roots of unity. And the roots of unity can be expressed in this form, which is x minus 1, x minus sigma squared until x minus sigma to the power of p minus 1. To better fit like the form, I can just change the x minus 1 to be x minus sigma to the power of p instead. And actually, you realize that if you manipulate by sub x equals to minus 1, and we'll get 2 is equals to product of 1 plus sigma to the power of I, where I ranges from 1 until p. So f sigma j is equals to 2 to the power of k for j not equals to p. Okay. Now let's consider when j is actually equals to p. If j is equals to p, we notice that sigma p is equals to e to the power of I 2 pi p over p, which is equals to 1. Which means that all of these terms are equals to 1. So since we have pk products there, f sigma to the power of p is just equals to 2 to the power of pk. So the sum in total is basically just 1 over p sum p j equals to 1 f sigma to the power of j is equals to 1 over p times 2 to the power of pk plus p minus 1 times of 2 to the power of k. And we can actually factorize out the 2 to the power of k to get 2 to the power of p minus 1 k plus p minus 1. And we can once again divide throughout to get 2 to the power of k, 1 plus 2 to the power of p minus 1 k minus 1 over p. And it was given that in the problem statement, it was given in the problem statement that 2 to the power of p minus 1 is not a multiple of p squared. So we can factorize out 2 to the power of p minus 1 to get all the way until 2 to the power of k minus 1 p minus 1. Which is then congruent to 2 to the power of k plus 1 plus 2 to the power of p minus 1 divided by p times k mod p. Then, so we can treat this like a constant, and all we have left to do is to find a k. Two to the power of k plus 1 plus some constant k is congruent to 0 mod p. And we can just do so by just choose k such that k is congruent to minus 1 divided by c mod p. And that basically solves our problem. So QED. Yeah. So for this problem, I guess the main takeaway was using complex combinatorics to actually approach the problem. And I think that it's a pretty standard technique. You can check out Tito Andreescu's problems from the book. This is under chapter 7, and the technique used was, if I'm not wrong, from example 4. Yeah. So do take note that for questions on subsets summing to a certain number or like being divisible by a certain number, a very good approach will be trying to firstly generate a function and then use complex numbers to actually and roots of unity to actually try and filter out the coefficients that represent the multiple of some prime number. Yeah.